participants from various parts of the globe. So I am Viju, Vice Chair of IAIEPLS Joint Chapter Kerala. Welcome all to this webinar. Today we have an expert in the field of renewable energy and microgrids for handling our webinar. We have Professor Josep Guerrero with us. He is a full-time professor in the University of Denmark, in the Department of Energy Technology, Aalborg University, Denmark. And his research interest is oriented to different microgrid aspects, including power electronics, distributed energy storage systems, hierarchical and cooperative control, energy management systems, smart metering and the Internet of for AC and DC microgrids, clusters and islanded mini grids, especially focused on microgrid technologies applied to offshore wind, maritime microgrids for electric ships, vessels, ferries, and seaports, and space microgrids applied to nano satellites and spacecrafts. Professor Guerrero is an associate editor of many IEEE transactions, and he has published more than 600 journal papers in the field of microgrids and renewable energy systems, which are cited more than 50,000 times. And he has received best paper awards in many IEEE transactions many times. And in 15, he was elevated as IEEE Fellow for his contributions on distributed power systems and microgrids. So with these few words, I invite Professor Guerrero to the webinar on AC and DC microgrid for offshore wind applications. So Professor, over to you. Thank you.
Yes, thank you very much for the introduction and also for the invitation to this seminar. It's my pleasure to present you here how AC and DC microgrid control has been expanding the last years in offshore wind applications. First, I want to also thanks also our Belux Foundations to support our center, and also the team members of our center. So you can see here, this is my email address, and then here you have my website as well. So our website contains all the information from let's say our center, but also you could see more let's say applications. Sorry. Hello?
Yes, sir.
You are audible, sir.
And here is our presentation of AC and DC microgrid control for offshore wind applications. As I said, you can find more information here also in our website. This is a little bit about our Center for Research on Microgrids, which are the research frameworks we are facing, like studying microgrid clusters, so a number of microgrids placing together, then maritime microgrids, we also have connection with this offshore IoT based microgrids and digital twins, and space microgrids. Yeah. Today we're going to focus more on this maritime. And this is also, I want to thank all our team members from our center. And also this is a picture from our lab facilities. We have some labs to test and developed a lot of controls. And we have also a test facility with real wind turbines and photovoltaic systems, yeah, in which we can take a lot of measurements. And this is a little bit about how looks, let's say, our demonstration house. Yeah. We have also a lot of interest about artificial intelligence. And you may hear that we have in our body like 3 brains. One is our mind, and then we have our heart and our gut. So basically we have here a lot of neurons, almost 1 billion. Then in our heart we have like 40,000 neurons, and then in the gut we have around 5 million neurons. So it's really a distributed control system. Also inside the mind itself, we have three more subdivision of brains. So let's say our reptilian brain, and then we have, let's say, the limbic system and the neocortex. So these three brains are also, let's say, having different, dealing with different aspects, let's say. Yeah, and this is, we have seen also how also these three brains coincide also very well with the seven chakras that your, let's say, and now because we are here with people from India, you know much better than me these kind of things, and this finally creates different kind of vibrations. Recently, some German institute, the Hermath Institute, they are observing how our heart and mind can be also more coherent. So let's say that if you are not feeling very well, excited, or let's say depressed, maybe there's no coherence between the waves in the brain and in the heart. But however, when you reach the coherence, you can see how it's you reach a constructive waveform. So I think that this is very interesting. Also, how they studied the electromagnetic field of the heart, which you can measure still with 4 meters at a distance, and allow you to synchronize also with some other people and also with animals. This is just one test that has been done in order to let's say, see how the heart rhythms were synchronized between a small kid and his dog. Yeah, you can see when this small kid enter in the same room of the dog without touching him, how these two heart rhythms are well synchronized. So that's, I think it's something very amazing. And we can see similar things happening also with the world, the electric world, let's say, how we are going more inside ourselves, let's say, to produce more electricity close to the demand. And this is the idea of a microgrid system. So basically having generation, storage, and consumption as close as possible. This reduces a lot, of course, the transmission losses. And then the next question is where we have to go. We have to go AC or we have to go DC. Yeah, this dilemma of AC or DC really impacted all the time the grid. And I will say that this happened a lot of this, let's say, dilemma when we talk about the small DC microgrid systems having naturally DC coupled solar panels, fuel cells, battery systems, and electronics. But at the same time, right now, we have a lot of inertia from the AC systems. Yeah, and the same thing we will see that is also, we can see now that is happening the same dilemma when we talk about offshore wind. Yeah, when we talk about offshore wind, of course, when we have long distances, several hundred of kilometers, then there is a crossing point in which AC doesn't make sense anymore, and DC starts to pay off. But of course, you need a certain distance. Yeah, you can see that indeed, when we talk about offshore connections, it's like extending a back-to-back converter. So basically splitting this and making a huge DC link. Yeah, and of course in the world, this is a little bit old, but it's happening a lot when we talk about HVDC, or for instance in China mainland, when they talk about ultra HVDC systems, trying to connect east with the west. And also here you can see some examples in the north of Europe, south of Europe as well, India, China again, and some connections in Brazil. These are only from ABB, but of course, if you cross with Siemens HVDC systems and many others that are appearing in the world, it's amazing how it's increasing the DC, let's say, when we talk about long line connections. And now we go back to a small world, let's say to microgrid systems. We have to understand that small microgrids, when they are connected to the grid, they have one operation mode, which is called grid connected mode. But sometimes we pass to islanded, or some of them are working in islands, so we have to fix frequency and voltage of the system. So it's kind of contradictory, one behavior and the other. Indeed, it's very dramatic when we have a grid connected system and without any plan, we just pass to island. Because if this system is just prepared to inject power to the grid, once it is not connected to the grid, then we may have problems of frequency and phase. and the system may work out of the frequency and voltage acceptable limits. So we have to start taking care of those two parameters. Yeah. So you can see just one example what happened when we have a battery system that can, for instance, provide the voltage and frequency, and a number of, for instance, photovoltaic systems that can work as the current sources. These systems will be stable by definition, but the main problem is what happened when I have, for instance, a number of energy storage systems trying to fix voltage and frequency working like voltage sources. They, of course, fight each other, and then we have to find a solution. One of the best solutions that I think that big electric systems give us intrinsically is the use of synchronous generators. So when we use synchronous generators, they are normally coupled, and they can, let's say, be synchronized without any kind of communication between them along a country. And this is amazing. How we do that is just by using what we call the frequency drop control. So you may know that this synchronous generator, when you increase the power, the speed is reduced. So that means that also the frequency is reduced. This means that there's an angle reduction. And then this coupling between angle and active power makes finally all the synchronous generators that we have connected in an electric system to be synchronized. We can have the same with reactive power, but it's not so natural. Yeah. So the natural coupling, what we also call inertia, is between our frequency or phase and the active power. So this is the inertia principle. When we have synchronous generators, this big mass in which we request more power, automatically you can see that depending on how big is this inertia, then we have less drop of this frequency. Yeah. This is just one example. This is from the book of Pravda Kundur, who already passed away recently, unfortunately. And I had the chance to know him personally here in Aalborg. You can see here what happened when we increase this power demand from the synchronous generator. Automatically, this frequency go down. So this means that dynamically the frequency go down, and then you still have in steady state a frequency error, right? Taking the same advantage, some previous European projects like VSync tried to integrate what it's called also virtual synchronous generators. This is to take the equations of a machine and to add inside a power electronic converter. So just taking a digital signal processor, implementing all the equations that the synchronous generator have, we could add inertia to the system. But of course, it was necessary to add as well energy storage systems. You can imagine that inertia also have implicit that you have some inertia. When you talk about photovoltaic systems, maybe you need to add extra energy storage elements. However, when you have wind turbines or wind power generators, you may have additional inertia due to the use of machines. Yeah. This is just one example. It's very famous. How we can couple a lot of metronomes, yeah, for music, metronomes together when they are in a mobile table. Yeah. You can see here, to start the experiment, we have all these metronomes. We start all of them out of phase, and then you can see, and this table is of course floating. So after some time, you can see how all of these metronomes are well synchronized. Well, there is one crazy here, but after some time, they are all synchronized. This is the same method that all synchronous generators use to be well synchronized inside the grid. So you can imagine that this floating table is like the grid, and this ball is like the inertia. This mass is like the inertia of the system. Yeah. So as we don't have inertia when we talk about power electronics converters, we have to emulate this inertia. And this is very easy by implementing those proportional terms, also called drop controllers. So as we know that in big power systems, the lines are basically inductive, then active power is coupled with angle and frequency, and reactive power is coupled with the voltage. So then what we do is we just do the opposite effect. Yeah, as when the angle increases, active power increases. What we will do is to measure active power and then reduce the frequency, which will reduce the angle. And we do kind of the same with the reactive power. This principle is very well known, and it's applied in microgrid systems, especially when you have a number of energy storage systems. Another important thing is what happens when I have a number of power electronics converters connected to a grid, and this grid pass to island mode. Once you pass to island mode, because of these droop controllers, then the frequency is going down. And then because this frequency is going down, or let's say that the frequency is dependent on the total amount of generation and consumption, then what we need is to establish a hierarchy of the control. Yeah. If you look at big power systems, they use kind of the same hierarchy of control. We have the primary control, which is basically the inertia of the system, which in the case of microgrids or power electronics-based systems, we have to emulate it. So this way, all this primary control is kind of a decentralized controller. It doesn't need any kind of intercommunications to synchronize all these elements. The next level is the secondary control, which restores frequency and voltage deviation produced by those droop controllers, and also synchronization. And finally, the tertiary control in our microgrid system is the energy management system to optimize the whole grid, let's say. The same procedure is used also in big power systems. So you can see here the secondary control. This is from our northern countries. So you can see that we were inside 50 Hertz, and suddenly we had here a jump. This jump, you can imagine that, for instance, could be sudden increase of the load. And then you had to restore this. How you restore the frequency? Just connecting new generation to the grid. And then finally, you reach again the steady state. Yeah. So this is what is called also the secondary effect, let's say, behavior. So in that case, you can see the primary response, and then the secondary response is just shifting up this frequency by injecting more power. So those are coupled, right? So if I inject more power, automatically I will shift up the frequency. This kind of controllers I can embed in a single, let's say, centralized controller. So like a SCADA system, measuring frequency and voltage, and then sending the setting points to each of my devices in my microgrid. Or I could use also local controllers sharing information and try to decide things. Yeah. So we have both ideas here. This slide, by the way, is taken from ABB. I think that this is very nice. Then from this concept, and this comes from one of our publications, we could have decentralized controllers in each of our units, and then intercommunications. And then here we have, let's say, the energy management system. What is under discussion, if it's this secondary control, could be centralized inside this SCADA system or distributed and use communication systems or multi-agent systems also to reach a level of consensus of which is the voltage and frequency of our microgrid system. If we are able to integrate hierarchical control system for a single microgrid, like the primary, the secondary, and the tertiary, we will be also able to interconnect a number of microgrids in parallel, and then form what we call also multiple microgrid clusters. Then this means that in the top of this primary, secondary, and tertiary control level of my microgrid, I can create a primary level of my cluster of microgrids. So it will be the distributed control of the different microgrids, and then another level to restore voltage and frequency here in my cluster of microgrids, and finally the tertiary to even have a number of clusters of microgrids and to balance the power flow between them. So this concept is very interesting because from this you can build a number of microgrid systems, and without having to remake all the communication system that you have inside the microgrid, you could establish a coordination control between those microgrids. Yeah. So I think that's very interesting, and I will point out at the end of the presentation how this is also happening in offshore wind. Coming from AC, we can see similar things on DC. So when we talk about virtual inertias, in our case, when we talk about DC systems, we don't have frequency. So that means that we just have two variables. It's basically current and voltage, or you could think power and voltage also. So this means that we can also integrate droop controllers by measuring the current and drooping down the voltage. The same way that we are using the Q, let's say reactive power versus voltage, here we can use current versus voltage in order to have those droops and in order to connect a number of voltage sources in parallel. Yeah, it's very important to see here also that we have a trade-off between current sharing and voltage accuracy. So the better the current sharing, the poor the voltage regulation. Yeah, so this is something that is intrinsical to the droop. In the case of droop control on DC, there are many other words to express the same. It's also called adaptive voltage positioning, but I will show this later. And also sometimes it's called virtual impedance. So the three concepts, it's basically in DC the same. I'm saying this because there's a lot of publications and reports that are confusing all these terms. Yeah. And the other interesting thing is that you could have also a number of multiple DC microgrid clusters. And this is also something very nice because you not only are able to control your DC microgrid, but also a number of microgrids in parallel. The way that we integrate the droop control, it can be different according to the different sources. So for instance, a solar converter or a wind converter, they can work both in maximum power point. Yeah, you can see here this parabolic effect between voltage and current means that the power is constant. But then if the voltage increases too much, then you can change to what we call droop control. Yeah, it's kind of a voltage source with some impedance. Yeah. And then about the energy storage systems, normally you will fix the voltage according to how much you are interested. And if you want to, for instance, charge or discharge your battery systems. And then we can have an interface converter connected to the grid. So it will fix how much is the voltage level in order to make your microgrid to import or export power from the main grid. Yeah, you can see here this picture. This concept comes from Virginia Tech. And what they did is to develop all these concepts, not only with a number of droop controllers here, but also with a what they call energy control center, which is sensing the power exchange with the main grid and to give, let's say, send information back to all the units. So similar concept of hierarchical control developed for AC microgrids can be also applied on DC microgrids, in which the droop control here is like a virtual impedance, and then we have a secondary control to restore voltages. Here we don't have frequencies, and then we have another level of energy management systems. Yeah, and this can be done also implemented, this secondary control, by means of a simple, let's say, PI to restore voltage in the microgrid system, or we could do it in a very decentralized way. Let's say we have a distributed control with their droops and the secondary control, and just using communication, we could restore altogether. Yeah. And also this kind of droop control, as I mentioned before, it's called sometimes adaptive voltage positioning for very small converters in order to also improve the transient response. You can see that those kind of spikes when you switch on and off some loads, for instance, a digital load like a microprocessor, those spikes could kill the electronics inside, let's say, all the CMOS that you have inside this microprocessor. And that's why if you use kind of a virtual impedance, you avoid to have all these spikes. So this is something that we are using the same principle in very small power converters. Yeah. Another important thing is to use what we call also DC voltage signaling. That means that depending on which is the level of your voltage inside your microgrid system, maybe means that your batteries are, for instance, empty or your batteries are full charge, etc. So you could have different states to signalize how all your converters will have to behave. So if, for instance, the voltage is going very high, maybe means that my generation is too big. The same with peak power systems with frequency. If the frequency increases, I know that I have too much generation. Here in a DC microgrid, I can see exactly the same phenomena. Yeah, so it's what we call also voltage signaling. Mixing this concept together with how we implement this primary and secondary control on DC microgrids, here you can see the droop control or our virtual impedance, how we can restore also with the same principle that I presented before, and how we can add another term in order to connect our DC microgrid to a main DC bus. Yeah. So this could be also another level of control. In that case, it's not an energy management system, but could be also connected to that. And you can see here some of the results we got. When we are using the droop control, you can see how the units are sharing the power, but the voltage is drifting down. And then another level, it's here to increase the load. And you can see that we have quite good current sharing. And then this is by using, let's say, the secondary control. You can see how the secondary control, every time we have a change, it restores the voltage back to the original. Yeah. And then we can also use this tertiary level to exchange power with this DC grid. This is the main concept here. Okay, I think that we have seen until now how works the microgrid control in AC and DC. Let us see how these microgrids concepts are right now shifting inside of the offshore wind. Yeah, because until now they were totally disconnected worlds. Yeah, microgrids and offshore wind. You have to think that we talk about kilowatt in one sense and megawatts in the other. So it's kind of difficult to see the connection. One of the projects we are doing right now called WindFlat is also called Offshore Wind Farms for Large Integration in Turkey. It's how we can connect wind turbines with their local controllers, what we call primary layer, connected to the offshore wind power plant control called secondary layer, in order to make them to work, let's say, not only as a current source, but also as voltage source, or what we call grid forming, to support voltage and frequency of the grid, and how we can also restore in this point of common coupling qualities like voltage quality, active and reactive support. Yeah. So we are using kind of the same principles in microgrids: primary control, secondary control, and finally tertiary control, which is the coordination control with other energy storage systems. So here we can see like a chicken egg problem, right? We have on one hand offshore wind farms, and we have on the other hand microgrids, right? So how all this is connected, I will show you some examples in which you can see what is happening. In the last few years, the number of offshore wind is increasing. This is the global cumulative offshore capacity in the world in terms of megawatts. So this is, we are talking now of around 30 gigawatt last year, accumulative. And this is impressive. It was really a vision of a dream. This is an old illustration from an hypothetical offshore wind in 1977. Yes, someone drew this as an inspiration, and then it became true. We have to think that many things are like this. Reality is something that we create from inside out. Yeah. So you can see that the first one, it was in 1991. Yes. So almost, let's say, almost more than 15 years after, it came the first one in Denmark. This was in Vindeby, which is close to Copenhagen. And you can see those wind turbines. This is the first in the world, by the way, first offshore wind farm in the world. Wind turbines of 450 kilowatt each, a total of 11, so around 5 megawatt. Yeah, something that today maybe we can have in a single wind turbine, we had to distribute in a number of wind turbines. So you can see from these small ones, from this, the first offshore wind farm of Bindeby, we talk about diameters of 30 meters. Right now, it was just this year, the implementation in the Netherlands of wind turbine like this, with a diameter of 167 meters and a capacity of 8 megawatt. I know that many other companies are also pushing to having bigger and bigger, but right now this is the last, let's say, implemented in a big offshore wind farm. So it's impressive. And it's not only impressive about how big are becoming, but also about how some countries are really pushing for wind, like Vietnam, Japan, and of course Taiwan. We have a very good collaboration with Taiwan. By the way, I want to give my greetings to Professor Su from Taiwan, in which we had a very good collaboration, and still we have, in order to establish these, let's say, very ambitious plans for offshore winds in Taiwan. You can see that in the next 5 years, it is planned to go to 5.5 gigawatts, and it will be in the horizon of 2035 that they want to have 10 gigawatt connected to this, let's say, a small and isolated island. It's really like a microgrid system, and they are making this dream come true. What happened last year, I don't know if all of you are aware, August 2019, it was a blackout in United Kingdom that led around 500,000 people without electricity. And then it was a short time, around maybe around 15 minutes, but it creates a big chaos because of metro station, computers, and so on were collapsed, and they had to stop all these, let's say, communication in the cities. So why it was this blackout? You can see a combined cycle plant from Barford. It was shut down. This was 727 megawatt, was shut down at 2 minutes to 5. And then after 2 minutes, the offshore wind farm, a couple of units of 406 megawatt units, or around 8 megawatts, went down. Yeah, and you can see here the effect. The frequency was 50 hertz, and suddenly here the combined cycle plant went down, and you can see how the frequency went down. And then after 2 minutes, the offshore wind was disconnected. Yeah, nobody knows the reasons. We just know the facts, and that nobody wants to be responsible, let's say. But what we know is that we need new ways of thinking about the control of wind farms. We need more support of frequency from wind farms, and we need that the wind farms work like a synchronous generator inside the grid. So this way the grid can see renewables like a power plant. Yeah. So this way we can do that kind of things. We are trying to do these things with this project that I mentioned before, WindFlag. You can find also more information here in this website, WindFlag ET AAUDK. It has been announced also in this magazine, Microgrid Knowledge, as one of the projects that try to apply microgrid principles in offshore wind. Yeah, I already showed you our, let's say, concept. And here you can see also, let's say, all our collaborators. Yeah, so I would like to thank all of them as well here. And here, what, let's say, apart from WindFlag, which tries to work more on AC grids, we can see that something is happening as well with DC. When you have offshore wind farms that are far away, you start to think about using DC. And if you start having DC and you have a number of connections, what we call some multi-terminal HVDC networks, then the main control that is used is also droop control, because basically you want to share power between one station and the other. So this way you can decide how much power comes from one station to the other and so forth. So you have a full control. There are many ways to implement a droop control for these VSCs that conform the HVDC system, like using, for instance, voltage and current loops, of course, using voltage loops without integrators. So you just droop it down using sometimes current or sometimes power instead. But finally, all these concepts, what comes is with the voltage versus current or power droop. Yeah. So this is basically the control that we can see nowadays that is massively, let's say, applied. I will not say that we have something already done, but it's right now, let's say, in the research phase. Yeah. You can see also some examples. This is from an idea in Greece in which they want to connect a number of islands in the Aegean Sea. And one of the possibilities is, of course, using HVAC. So this is the conventional connection of wind, offshore wind power plants. And also we have the connection to the island networks with wind and other renewables, as well as local generators. And you can see here on the AC connection, what we need is a couple of, let's say, converters to compensate reactive power and or active filters. Yeah, this way you can compensate reactive power and also potential harmonics. We have a similar thing if we think about DC. However, we may not have this kind of compensation of reactive power or harmonics, of course. And this is how they solved finally. It's a 5-terminal HVDC topology. I think it's very attractive because here you can see, for instance, a couple of grid connections through HVDC. And then here you have 3 generators coming also with this DC link. Yeah. And finally, you have here like the HVDC grid controller. As you can imagine, inside these boxes, what we have is droop controllers, the same, very similar as we have in DC microgrids. In that case, you can see that sometimes we have slack buses. So that means that we fix the voltage. It doesn't matter how much is the power inside some limits. Sometimes we define voltage margins. But when we want to have power sharing, we define also voltage versus power droop functions. And we could have also some dead bands. For instance, that our system can work in constant power mode between some possible voltages. And then it can droop down when we just decrease this voltage, automatically power go down, and vice versa, right? So this will be, let's say, the droop operation mode in that case. So you can see how also on DC, we can see a lot of, let's say, synergies on what for many years we have been developing in microgrid systems. When we talk about AC, why we think that also microgrid control technologies can go also for offshore wind. First is like in offshore wind, we use type 4 wind turbines, which means that basically all these turbines are connected to full equipped converters. So this means you just rectify and you just use an inverter. So the, let's say, wind turbine side and the grid side are to a large extent decoupled. So we can add many of the ideas in the inverter side. One of them is to use islanded and black star operation. You have to think that sometimes the offshore wind farm needs some reparation. For instance, the cable can be broken or cut in some moments, or you could have some blackouts outside. So because of that, you need to be able to operate in island conditions, because otherwise it will take very long to restart the whole wind power plant. And then once you want to restart it, right now, nowadays, unfortunately, diesel generators are required to energize the power plant. This is something that is against the philosophy of promoting renewables. And that's why we think that also black star operation needs to be there. The third point is virtual inertia. A lot of these offshore wind turbines add virtual inertia inside their power converters, and this is connected at the same time with droop control. So we believe that by using virtual inertia, it's kind of drooping your system. So this way you can improve, let's say, the frequency response of your offshore wind farm. We can provide at the same time voltage and frequency support thanks to the use of grid forming inverters. Right now, the big discussion is, should we use grid following inverters like now, or should we shift to grid forming inverters? There's a lot of discussion. Recent studies said that maybe a percentage of your wind turbines could be working as grid forming inverters. But another possibility can be that normally your inverters work like grid following. And once you see that there's some event in which the frequency goes out of the normal ranges and you predict that something may happen, you could switch to grid forming control. And the other big question is, if we want to do all these things, do we need extra energy storage? And the answer is yes, we may need additional energy storage if we want to really perform all these features inside our offshore wind power plant, like happened with microgrids. So you can see this is from an ongoing project right now. Some colleagues from DTU and Valencia and many other universities and companies are trying to provide black star capability and islanding operation for these offshore wind plants. And they define different levels. Like one is more self-sustain in the, let's say, wind turbine level, adding battery systems, but also additional self-starts for those wind turbines once the blackout occurs and then they want to restart. The next level, it's, let's say, the parallel operation of all those systems. So we have the parallel operation together with the grid and between them. And the next level is to have a grid forming offshore, some of them, for instance, connected in parallel, in which they are able to form a grid. And then from the DC, you could also connect to the AC, right? This concept, they are working a lot on DC, but I will say that it's possible to export as well to AC. Yeah, this is just one of the examples from our colleagues in Valencia working in this project. You can see that there's a number of wind power plants. In that case, there are 3 offshore wind farms working, each of them with 400 megawatt. And then you can see how they are interconnected between them and then forming, let's say, a connection with just with diode rectifiers, which is a very cheap solution and reliable, and then having a connection in DC to this main converter. Yeah, here is very interesting to see how they are using also classical, let's say, microgrid controllers. On the one hand, they are using distributed droop controllers. You can see here the classical frequency versus active power droop in order to share the power between wind farms. And then the other is to use the reactive power versus voltage droops in order to share reactive power as well, compensation. Yeah. And then we have a centralized power controller, which normally we use this in the secondary control or even in tertiary controls, just in order to make how many, just to fix the amount of power that you want to inject from your offshore wind power plant to the main grid. Yeah. And I will say that this is very nice how this is working. When you take a look on the wind farm control, you can see that there is, of course, because we talk about a power plant, there's a lot of parallels with the microgrid. You can see that we are measuring the grid here, and then we send those commands, frequency, active power, and here you have voltage and reactive power with those blocks with frequency control. And then we have another block of active and reactive power controllers that is sent to each of the wind turbines by means of these active power and reactive power dispatchers. Yeah. So it's kind of, you calculate how much is active and reactive power from the previous, you adjust according to the frequency and voltages and according to how much is the system operator request, and then you can distribute those dispatch signals. You can see that here we have again a wind farm hierarchical control. So indeed, this block, what we call wind farm control level, if we see inside, what we have is the number of control functions like reactive power control functions, like voltage support, reactive power control, and the same with active power. Yeah. So this way we have the signals from system operators. We send these references, and then these references are contrasted with the measurements in the PCC. This is something that also we developed for microgrid systems, in which we compare the active and reactive power that we had in the PCC with our desirable active and reactive powers. Yeah? And then you process it to the main controller, and then you send to the dispatching. Yeah. Finally, to show you something else that is happening right now, this from a very very last publication from this year, in which it's proposed to have decentralized control between wind power plants. Totally centralized control. So you get all the information and you send the reference back. Having on the other side totally distributed control. So this means that we have decentralized controllers, and then interchanging information, you can reach a consensus, or a hybrid control, just mixing that some of these algorithms are centralized, and some of these algorithms are decentralized. The same as we have seen with microgrid control many years ago. And you can see that is happening the same, that right now offshore wind power plants and in general wind power plants are starting to think in a more large vision, in which you could have a clusters of multiple offshore wind farms or clusters of land-based wind farms. This is something that we already envision for microgrids, and it is happening right now also for wind power plants. Yeah, I think that's all from my presentation. I just want to finalize with a sentence from Donald Trump. He said, "I never understood wind." So that's why now I understand a lot of things. Thank you very much for your attention.
Professor, for the very enlightening session. And now it's time for Q&A. Over to Eldo. Eldo, could you please
Yes,
read
sir.
out the questions?
We do have many questions here.
Yes.
Let me read out them. Can we generate a massive voltage by connecting small dynamos in parallel, or there's a limit on voltage?
Well, if you connect a number of dynamos in parallel, of course you can increase the voltage. So I will say that theoretically, if you are able to balance well the voltage outside the dynamos, we could reach higher levels of voltage, the same that is happening with converters. However, dynamos has a very low efficiency. That's why right nowadays we don't have so many dynamos in the market. It was in the past with electric, the first, let's say, ships 1 century ago, they work with DC, let's say for illuminate and to use many electric parts of the ship. You can see one of them in San Diego, and they use some dynamos, but I don't think that you could see a lot of these things anymore. So right now we are talking more about stacking converters, and concepts like MMC appears in the market, or let's say in our field, thanks to stacking a number of DC converters.
Thank you, sir.
Yeah,
Next
thank you.
question. What is the current control problems in the multi-microgrid?
Yeah, if you have the current control, you said.
Yes, sir.
Nowadays control, you mean? Or it's the current about the current, you know what I mean? Should be nowadays, no?
I think they meant about current control.
Yeah,
Current,
but
electric
when they
current.
say
In
electrical,
in multi-microgrid.
yeah, in electrical, it's clear that if you have a number of microgrid systems connected, forming clusters, you may have harmonics maybe flowing between them. That's why many times maybe you use transformers in between. So when the distances are more or less long, but I will say that is basically this because if you have a number of power electronics converters just connected in parallel, maybe some of these power converters are very well designed, but once you put all of them together, maybe you could start having resonances and they will start interacting each other. So this can be multiplied in if you have a multiple microgrid systems and you don't have isolation. Yeah, thank you.
Thank you, sir. Next question. Can you discuss more about virtual inertia and how we are going to achieve it?
Yes, virtual inertia is one of the things that it's more attractive, let's say, especially when you think about offshore wind that you have type 4 converters. So that means that full rated converters. And virtual inertia is possible because you have to imagine that your machine is rotating and then you still have some inertia that you could use to inject extra power to the grid. Of course, this is a problem because if your rotating speed, if the speed of your rotating part it's going down from 70% of the nominal speed, it will be very hard to recover again, and maybe your wind turbine will have to be shut down. So I will say that that's the main problem. If we want to still increase more this virtual inertia, the use of energy storage, it's mandatory, I will say. But I will say that right now it's going to be very useful if we want our wind farms to act as a power plant, as a conventional power plant, from the sense that they participate on voltage and frequency as the others. It will be a must. Yeah, thank you.
Thank you, sir. Next question. How power quality issues like harmonics affect the offshore wind generation?
Yeah, of course, there's a lot of issues there because you have to imagine that those cables, we need to compensate reactive power. This is expensive because you can do it with, let's say, passive filters. But sometimes, let's say that if you want to also add or subtract a huge amount of reactive power, maybe you need additional STATCOMs. And then, of course, this talking about reactive power and voltage, but then at the same time, we have the harmonics problem. So you have background harmonics, you have the harmonics that also the same converters of the wind turbines are also injecting. You are connecting all these systems in the grid, and we expect to see a lot of what we call interharmonics. So this means that not only we see the harmonics, the typical classical fifth, seventh, even odd harmonics, but also you can see harmonics that are in between due to these interactions. So it's really challenge how we are going to adjust those filters and which kind of alternatives we will have in the future. Are we going to also have possibilities of helping, thanks to the inverters connected in the wind turbines? This is something that is really unknown because we have long distances between the wind turbines and the point of common coupling, transformers, long cables, and so on. So it's hard to imagine that really you can do something at such a long electric distance. So this is one of the biggest challenge, how we can avoid this kind of interharmonics that finally, in many cases, made us to stop also wind farms. And this is something that happened in another example in UK. They had to totally stop a wind farm due to the harmonics. So it's really a problem that we faced in a previous project and we're going to face in future projects. Yeah, thank you.
Thank you, sir. Next question. What is the impact on self-healing of microgrid?
Sorry, what?
Self-healing.
Yes, but what is the question exactly about the self-healing?
Self-healing of microgrid.
Yes, but what is the question about? Self-healing in microgrids is very wide. What do you want to know?
Ananda, could you please narrow down the question? You can post it in the chat.
The question posted is, what is the impact on self-healing of microgrids? That's a question in the chat box.
Okay. Yeah, so basically, if we talk about self-healing microgrid, I will say that it's more a microgrid which is able to heal itself. And I will say that in the past, it was more connected to the protection system. So you are able to connect or disconnect some part of your microgrid and then to reconnect again, for instance, when you have a short circuit. Yeah. But right now, I think that because we can see a lot of natural disasters, we are going to another level in which we want to have unprecedented levels of resiliency in places like, for instance, Indonesia, or many other places that corresponds to the ring of fire, in which you could have tornadoes, volcanoes, heavy rains, floods, and so on. So it's more related on how we design the microgrid, but also how we are going to also heal not only the electric parts, but also some other mechanical parts. So I think that this is something it's a very complex issue, but I will say that right now there's a lot of efforts to have this kind of microgrids that are able to ride through after a natural disaster happen. Yeah, thank you.
Thank you, sir.
So you can
so next,
along with that, ask the last question for the time being. You can
Yes.
see a second question there, right? Eldo, what's your suggestions on? Prof,
what's your
yeah.
What is your suggestion on research problem on microgrid to researchers?
Okay, my advice for the ones who try to find the research question of microgrids, I will ask you, what do you want to solve and why? Because I can see that it's a little bit dangerous that you start to search in internet for problems. You will find a lot of problems, but maybe none of them will be realistic. So I will say, try to approach a facility in which you can find a microgrid and try to help with your research to solve the problems that those microgrids have. Otherwise, you will be in trouble to run away from what is happening right now. So my advice will be, try to see which is exactly the application that you want to solve, because I just show you here 4 of our frameworks. We work with microgrids that are land-based. We work also with microgrids that are placed in ships. We work with microgrids that are also in space or in satellites. And the problem is totally different from one to the other. So, and it's very attached to the technological problem. So I will say, first, try to find your study case. And if it's possible, try to find a person who's in touch with this study case. For instance, from our center, we can provide you a lot of information and data. So I would like, from the ones who want to try to find problem to solve, just contact us and we will provide you a list of problems. There's a lot and we cannot tackle all of them at the same time. Yeah. Thank you.
Thank you, sir. Next question.
Can I take
yes,
over, Eldo?
Yes,
So
sir.
thank you, Professor, for the nice replies to the questions. In fact, we have a few more questions left, but due to the time limit, we will be taking the rest of the questions through mail. We will send
Yes.
you the questions, and yeah, you can reply via mail.
Yeah,
And
exactly.
I request
Excellent.
Dr. Vasanthi, the Secretary of IAIEPLS Chapter Kerala, for the formal vote of thanks. Over to Dr. Vasanthi, please.
Thank you, sir. I thank Professor Joseph for his wonderful presentation on microgrid control for offshore wind applications. Really, it is a breakthrough to all the participants who wish to pursue research in this area. And thanks a lot, Professor, from IAIEPELS Joint Chapter Kerala. Also, I thank all the participants who supported us by actively attending in this webinar. And also, I thank all the panelists who worked a lot behind this to make this great event. Thank you.
Thank you very much. It was my pleasure. And I think that you did it a very good job. Without your help, this will never be possible. Thank you.
Once again, thank you all participants. You got very good participation and very good interaction. So thank you.
Yeah, thank you. Thank you to
So
all
hope,
of you.
yeah, so hope to meet you in Kerala sometime later. Thank you.
Thank you. Thank you.